supervised in some way. It's supervised by taking in information about the world. So, but yeah, good question. Anyone else? All right. Oh, that's where we are. So the next one is human capacity cognitive computing. I'm going to take my jacket off because this is mostly about semantics, and academics don't typically wear jackets, at least not in the US. So once again, that's me, and we are where we are. So some stuff about cognitive computing here. It's a huge market. People are going to be more and more using cognitive computing services, but how exactly is it going to work? We just talked a little bit about that. And what is cognitive computing anyway? We talked a little bit about that. When I tell people that I work on language understanding, I get this question a lot where people see, there's deep learning research going on. A lot of it's happening in the vision space, people processing images and videos and stuff. Some stuff happening in the language area. It's becoming more and more popular. But you don't see as many papers at conferences about language as you do about vision. So people ask me, like, which is harder? Is it harder to process language, or is it harder to to do vision? And some people think, like, don't we have language already figured out? Like, I can talk to Siri on my phone now, and isn't that just sort of a done thing? And so it's not that interesting, and so not that many people are writing about it. I don't know, who thinks it's an easy thing that we've already figured out? Yeah, nobody. You're not taking the bait. All right, good. You're a tough audience to fool. So I just, when people ask me this, I say, look out into nature and, tell me which one you see more in nature. Do you see, a lot of animals that can see, or do you see a lot of animals that can talk? And, of course, the answer is lots and lots of animals have eyes and they can see. And that's something that nature figured out very quickly, and it gave creatures an adaptive advantage, and so tons of creatures can see. Talking, however, is something that, unless they're in cartoons, animals don't typically do. Now, you might say, well, there are all kinds of different communication systems, right? We know that dolphins and whales communicate, birds have bird songs, bees communicate through dances about the location of flowers and stuff. But I would argue that humans have developed a very unique communication system that is very different from the kind of communication systems that we see in animals. And it's something that has been called sort of the human capacity. So what are those things that humans can do that we don't see in the animal kingdom? Well, one is that we communicate in multiple modalities, okay? And so what I mean by that is we can talk, as I'm doing right now, with sound. I can also talk and point at the same time. So I could say, hand me that, without even touching it, and say, hand me that cup. Or I can say, hand me that, and point to it, and the gesture now replaces the word cup. But all these things, for humans, get fused into a single semantic representation, and we can go back and forth between the two very easily. In fact, we're so good at that when people completely lose their ability to hear and to talk, they can still communicate in a gestural language that has all the full range of meaning that we get by talking. So we're able to go back and forth between the two modes very, very easily. And this is something you don't see in communication systems in the animal kingdom. So the second cool thing that humans can do in communication is that they can embed semantics and recurse those semantics over long sequences. So an example is this little sentence here. This is the rat that ate the malt that lay in the house that Jack built. This is from, I don't know if you get this in the Italian version, but there's a very popular children's book called The House That Jack Built. And as you turn the pages, you just get more and more of the same sort of phrase getting embedded, and so then you get, this is the farmer, blah, 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 that lay in the house that Jack built. And so this leads to our sort of third point, that aside from just recursing an idea, we have the potential for what Humboldt called the discrete infinity, or the infinite use of finite means. So we only have a certain number of letters in the alphabet, we only have a certain number of words in our vocabulary, and yet we can potentially communicate infinite numbers of messages because of this embedding capacity, the ability for us to embed and recurse over sequences. So these three things, multimodal communication, recursion, and discrete infinity, define what has been called the human capacity. And I didn't invent that. It actually came from an anthropologist back in the 80s. But we've co-opted it for our cognitive computing sort of idea, because these three ideas are fundamental to our notion of what you really have to think about in order to design an architecture that is going to think in the same way that humans think. So, humans only started talking about, the estimate is maybe 30,000 years ago. And people wonder, people are still wondering, why did we start talking? Why did language develop? It obviously gave us some kind of evolutionary advantage. So there are sort of three possible sources that we might have gotten this ability from. One is there might have been some kind of change in the interface. Maybe we developed something in our hearing or in our auditory processing that allowed us to process language in a way that other animals can't do it. Or maybe it was something in the vocal cords or something. So that's one possibility. Another possibility is maybe we got some different learning algorithm that allowed us to do these things in a way that animals can't do. And the third possibility is maybe all those things are just the same, but we have a different architecture. The brain is just suddenly got wired in a way that allowed us to learn language in the way that we do. Now, the interface, they've analyzed this, and it seems like other animals, some other animals at least, have most of the same equipment that we have and could probably, communicate more or less similar to how we do. The learning algorithm, we know that neurons are the same across all the different species, and so learning algorithm doesn't really seem like a good place to look. Architecture, on the other hand, is something that all animals have very different architectures in their brain, and the architecture of the human brain is particularly interesting. And this is an area where deep learning is very interesting, because with deep learning you can sort of play around with different architectures and see what you can do to try to make a neural network work in the same way that the human brain seems to work, and try to get at this sort of these human capacity abilities. So one good example of that came from Jeff Hinton, who's like one of these guru founders of deep learning, was doing neural networks since the 70s. He published an interesting paper in 81 and another one in 86, where he was able to establish these neural networks that would learn things like John hit Mary. So you've got an agent, and then a relation, and then a patient. And they basically learned through a neural network representations for all of these by creating these sort of assemblings where you'd have a role, a relation, and another role, and then you would have a neural network that would learn all these things. And then it was able to, sort of produce an output that, seemed to be something like what humans would do. But it was able to learn this sort of agent, relation, patient thing. It was a really cool experiment at the time. I always thought, it's kind of a hack, because you actually have to create an assembly for an agent and an assembly for the relation and then an assembly for the patient. So you're kind of forcing your neural network to have an architecture that you probably don't actually have in the brain. At least that was what I thought until, 2 years ago, 2015, when some folks at Harvard actually published a study where they did fMRIs, a very clever patient study that I won't go into right now the way they did it, but they basically threw fMRIs discovered the locations of the brain where this agent, patient, and relation things are actually happening. So the answer is your brain does actually have architectures that figure these things out. And that's Franklin and Green 2015. If you want to look it up, it's a very cool thing. So just to recap, language is in fact very hard, even though we all do it every day and it seems very easy, but it's not an easy thing to figure out how to teach a machine to do. And what we're calling the human capacity probably arises from some special architecture, and whatever learning algorithm you're using, we can probably just play with different architectures to eventually figure this stuff out. So I want to talk a little bit about semantics, and semantics is just figuring out what stuff means and how do we know what things mean. So an example that semanticists like to use, for some reason they are always talking about the term bachelor, maybe because semanticists are mostly bachelors. But they always use this sort of, so words can have different senses, and so one word that's popular among the semanticists is this idea that you've got a bachelor like this guy with the rose here, and another sense for the word bachelor is a male seal that is not yet mated, somewhat similar, but you've got in one case a man, in another case a seal. And so, in the sort of 60s and 70s, you had this dictionary approach where you might define one sense as, a physical, human, male, never married, blah, blah, blah. And in another sense, you might have a physical object that's an animal, it's a seal, doesn't have a mate, blah, blah, blah. And so you define each sense of the word through these semantic primitives. So this is from a book from about 1975. And you could take those senses and then define them in a tree of features like this, where one sense of bachelor kind of follows this side, the other sense follows this other side. This is from Katz and Fodor, 1963. And then you might represent that. This is what we call sort of a units representation, where I might have some long feature vector of different features like noun, human, animal, male. And so on the top one, we've got bachelor number one, which is a noun, a human, a male, blah, blah, blah. The bottom one, we have a different units representation. You could also put it in sort of a matrix representation like this, where we've got the different senses, and or you can put it in sort of a vector space representation where we've got all the various features in some high-dimensional space, and each of the senses is plotted in this high-dimensional space. And I just put it this way because these are three different ways that you'll see these things written or represented in the literature as either units or matrices or vector space, but they're really all just different representations of the same thing. So there are a bunch of problems with this sort of dictionary approach to semantics. One of them is you need to have these necessary and sufficient features to define the thing that you're trying to define. But most of them are not necessary or not sufficient. Eleanor Roche in the 1970s wrote some great papers about prototypical examples. She did some interesting psychological experiments where she found that people thought of a robin as being a representative bird much more than they thought of a finch or a penguin. So people don't really categorize things as easily as you think that they might doing the dictionary approach. And then our language has, colorful metaphors, and it's analogic in ways that, these dictionary approaches don't really capture very well. And then Charles Fillmore talked about these edge cases, like, a widow is somebody whose husband died, but do we call her a widow if she actually murdered her husband? In those cases, it technically fits the bill, but we don't really call that person a widow. Another great one comes from Herb Clark, who has this great example of Max went too far today and teapotted a policeman. Now, it's a sentence that you may never have heard in English, but it's a perfectly reasonable sentence. And if you knew the contents, like maybe Max went around with a teapot and would pour tea on policemen when he saw them, or on random strangers, I could say this sentence to you, and if we share that idea about Max, it's a perfectly sensible sentence for you to say. But it's difficult to define that kind of sentence in the semantics that we were just talking about. So another approach to semantics is what they call the distributional approach. And that's that maybe we just figure out what words mean by the other words that are around them. So we can take a little window here. We have the quick brown fox jumped over the lazy dog, and we can look at windows of 3 words, use that to make up a matrix here of which words fall inside those windows. And these words on the left here are what we call the context features. It's really just the same words as what words fall in the window. And then we can use some kind of dimensionality reduction or compression, as I was talking about before, to collapse these context features into latent factors or what you might call microfeatures. So we might collapse those and then get some kind of matrix that looks like this. And that gives you distributional probabilities for words occurring within this particular sort of semantic microfeature. So this was the kind of representation that we had before. We call it a local representation. We can supplant that now with what we might call a distributed representation, where you have all of these sort of latent features. And something that before we were representing as just young might be distributed across several of these features. Or you might also see it in this vector space representation, again, distributed among these latent semantic features. And so when you're doing deep learning on language, you can learn these distributed representations by using neural networks to approximate the kind of matrix that I just showed you. So we learn from data as it comes in. You learn it over sequences like sentences or audio streams coming in. And you learn from lots of context features, not just the other words, but if you have images or that sort of thing. You might have visual features. You might have some kind of structure that you get from a parse tree, that sort of thing. So in that way, we can actually learn sentences like Max went too far today and teapotted a policeman. And if we're talking about a teapot earlier in the same story or whatever it is we're reading, a distributional, deep learning based approach will actually understand the word teapot in the right context. So there's a great story that Charles Fillmore told about some children who were with their teacher, and the teacher took out a grapefruit and started peeling it. And the children said, "Oh, it's an orange. You're eating an orange." And she said, "No, it's a grapefruit." And they said, "No, it's not a grapefruit, because a grapefruit, you cut it in half with a knife and you eat it with a spoon. And an orange, you peel like this." And then she explained to the children, "No, you can take a grapefruit and you can peel it and eat it like an orange." But in the minds of the children, an orange was defined by this contextual feature of peeling. It wasn't just the fact that it was orange and round, it was also the way that you eat it. And so this is how children are learning all the time, is they're taking in all these taking in all these contextual features and defining their own semantics with them, and then learning and revising those as they go along. So in human capacity cognitive computing, using sort of the principles that I showed you in the first talk and the principles that I've showed you here, there's a huge potential for learning all of these contextual features from your input space. And your input doesn't just have to be, as I was saying, visual features and audio and stuff like that. You can use all kinds of sensors and stuff and create and we can learn these sort of complex memory assemblies using RNNs or LSTM or GRUs. If you don't know what these things mean, start reading the deep learning literature, and people are talking about them all over the place. So just to sort of sum up, a human capacity cognitive computing platform will look something like this. Okay, it handles contextual features in the input from multiple modalities and projects those into some common representational space, as I was talking about in the first talk. It will support various types of architectures with sort of specialized assemblies, like I was showing you from the Jeff Hinton example, that permit this kind of recursion and embedding, and also this kind of multimodality, and also support sort of the principle of discrete infinity. And because of its capacity to do all this, it will have this fluid ability to interpret new meanings and learn things, learn new information as they come in in the same way that people do. And this is our little plug here at Loop. We've got this GPU-based appliance that does human capacity cognitive computing and learns from both unstructured and structured data, and from that produces some kind of structured representation. So that's the end of the second talk, and I'm 15 minutes ahead of closing time. So we've got time here for some more questions. If you've got any questions or comments about this talk or even the one before it, or anything else. And this, of course, is Commander Data, who I think, was not programmed very well. If he has to ask a question like this, he didn't actually ask this on Star Trek, but it's the kind of thing that he would ask. And it makes me think that Commander Data was programmed just using the old way of doing semantics and not the sort of human capacity cognitive computing way. If he were, he'd never have to ask this. No other questions? All right. Thank you.